Just a little heads up there. But yeah, we're going to be going over nucleic acids and their structure and their functions and functionalities and how it's much more diverse than what you learn about in biology. So, because what is the structure of? Well, first of all, what's an example of a nucleic acid? Pardon? RNA. Okay, what's another nucleic acid? DNA. Okay, are there any others? Oh, we hear yes. But it's a hesitant yes. What are some of the others? Or what are some of the types of nucleic acids?
tRNA.
There's tRNA. There are the microRNAs. Pardon? rRNA, ribosomal RNA. What else? mRNA. There's the snRNA. miRNA. No. But we're going to find out that there's even more. And so, we've already said T, but there's also, let's see, we didn't say snow RNA. We didn't say peewee RNA. And so there's peewee. Not kiwi, peewee as in Herman, but spelled differently. See, you get to find out a lot of different things here.
Peewee, heart, wow.
And so,
Somebody had fun.
oh, you wait until you find out what peewee RNA is about. Some will be cringing and some will be having lots of fun with it. Let's just say it has to do with the male genitalia.
Oh.
Okay. I'll leave you on a cliffhanger there because that's towards the end of this semester. Now, I know, I see a couple of cell phones, everybody out there, and you're like Googling peewee RNA. So, but, yeah, you may get blocked by Southeastern whenever it brings up some of the topics for peewee RNA. Let's just say, yeah, peewee. You can kind of imagine what that has to do with respect to the male genitalia. Okay, so this is in generic nucleic acid structure. You should know this by now, and the fact that it has a phosphate. There's a phosphate, there's a sugar. It is what kind of sugar is it? Besides a pentose, what specific type of pentose is it? It's a ribose, okay. What else? What other classification can we give that sugar as a review for sugars? It's a what?
Beta.
Okay. What else? Whatever is broad generality.
It's a furan.
The furanose, that's what I was looking for. Yeah, this is a furanose because of the fact that it's cyclical and it's 5. Okay, and then there's going to be either a purine or pyrimidine base that's attached. And these are all nitrogenous bases that are naturally occurring. And so you should know the generic structure of RNA versus DNA. And is this one RNA or is this DNA? Okay, I was hesitant. Why? Why do you suppose that this is RNA? It has the 2' hydroxyl group. And then this would be the anomeric carbon, by the way, the 1'. Okay. These are the parent compounds for the purine and pyrimidine. I don't require that you memorize their structures, other than the fact that you can remember that which ones are purines versus pyrimidines and which one is a single cyclic group versus the bicyclic group. And so which ones are the purines? A and G, and then what ones are the pyrimidines? CT, U. What about, are those all the bases before you even get to the, not including modified bases like methyladenine, methylguanine, stuff like that? Now there's also inosine that we'll talk about, and then there's some of these others like dihydrouracil. What?
I feel like you just went against everything I've learned in the past.
I know. Like that commercial where the blows her mind. So yes, and you're gonna find out that there's a if you wait till we get to non-canonical, okay, versus canonical. All right, so these are the purines. These are the commonly naturally occurring purines and pyrimidines. So this is A and G for adenine and guanine. Of course, C and T is cytosine and thymine. Thymines in DNA naturally, and uracil is in RNA. Is there ever uracil put into DNA? By accident sometimes, and so we have ways to get rid of it, okay, which we've been studying hopefully in chemistry of cancer, okay, where things get misincorporated, because if not, bad things happen and people die, and so, yes. All right, and the way, of course, I went to the University of Missouri, which the biochemistry department is through the ag school, and so the way that they taught us was the Aggies were perfect, for AG. Purines, perfect. Ah, yeah. Now, oh, there's the light bulb's coming on some of your eyes. I think some of you haven't woken up over the 3-day weekend. And so, okay. And as we've already mentioned this one, we've already know that this is the RNA, and we can tell that because of the fact that the 2' hydroxyl group is still there, whereas if it's a DNA, what's in its place? It's just a hydrogen, okay, and so there wouldn't be this, it would just be a hydrogen if it was DNA. Okay, and it technically did arrive from an aldose. Now, as I hinted before, the bases can be modified. Now, are they ever modified in DNA? Yes. Okay. Why? Why are they modified in DNA?
For transcription regulation.
They can for transcription regulation. What else? Why else would they be modified? They can be inactivated or activated, for that matter. What's another possibility? Maybe not for us, but for certain organisms. Why would they be modified? So I'll say something that's going to be kind of sacrilegious to some people. I see that. That kind of gets some evolution. Oh, that's like the Miss America kind of question, almost like stability, evolutionarily.
Well, wouldn't it be for like bacteria, pathogens?
So bacteria do it. And so why? Why does it? Why I say it can be sacrilegious to some, would probably be sacrilegious to Dr. McConkey or Dr. B. But why do bacteria modify their DNA?
So that bugs would kill us.
Well, it's not like they're thinking, this little E. coli is thinking, I'm going to go kill Jackie Burke. Oh, I'm going to have to erase that part. No one heard that name. What?
To become resistant?
Well, in a way, and I'm going to use a term that they're going to probably cringe at. It's sort of like their immune system, because they have to be able to tell their DNA from other, not just host DNA, but other, phage and things like that can affect them. And so they modify their own DNA, and they can, maybe they methylate certain bases and another strain doesn't. And so I know it's not really an immune system. That's why I say that they would find that sacrilegious, because it would have a microbiology term for it. But I'm not a microbiologist, so I call it their immune system. But they have to be able to recognize their own DNA. This is one of the reasons why, if you ever look at, and for those who are in genetics, or have taken genetics, or the TA for genetics, and you have to look at things like this, that the restriction endonucleases, sometimes they'll have like star activity, or they'll have some special, like they require methylation or they don't require methylation. It's because the parent bacterium that it was cloned from either required the methylation or didn't require methylation. And otherwise that enzyme wouldn't recognize it as being the DNA that would belong to that organism. Okay, but these are just some of the examples. And then what about RNA? Is RNA ever modified? Yes. Is it modified in humans? Definitely. I mean, we have lots of modifications. There are so many that are out there that it's just almost, it'd definitely be impossible for us to cover in the lecture here. And there are people that do nothing but study these. And many of them have their own metabolic pathways and that are required for life. I can give some examples later on of how specific some of these modifications and are, to where if it just literally cuts on one side of the atom versus the other side, we would die. And so, which, by the way, especially in biochem, too, we find out that we can die easily a lot. So, life is precious. gift from God, faith integration. So, all right. So these are just some of the others. Methylation are easy. You know, they can be acetylated. They can also be reduced or oxidized and things like that we've seen. Alkylated. And I do want, because some are currently in organic chemistry now, but I wanted to point out, like, for example, this N6. The reason, what that means is the N is a locant, and technically it is italicized to let you know that it's a methyl group that's on that nitrogen, and this nitrogen's hanging off of carbon 6. So that's why it says N6. Sometimes it makes like N4, N2, for example, like that. And so once again, the N2 methylguanosine, that just lets you know that it's the amine that's methylated, and that amine was attached to carbon number 2. Otherwise, it's like 5-hydroxy really does mean 5, that's on carbon number 5. It's a hydroxymethyl group instead of just being a regular methyl group. Okay. And nitrogen's not the only one that can have a letter as a locant. Technically, you can also have oxygens, so you can have an O that can be modified and have things hang off of it, for like ethers and things like that. Or you can have sulfurs that can be modified. And then the locant would be an S. And nucleotides, normally. So here's some that are the modified tRNA bases, and if we can gather Caitlin's head back together to reblow it again. This is the inosine that I was talking about. It's related to guanine. Okay, and it's given the letter I whenever they write it in many times. This is pseudouridine. Pseudouridine is in every tRNA. You're going to find out. It's required. It's very, very important. The symbol that they usually give it is a little psi symbol. And then methylguanosine and thiouridine. And the thiouridine is one that actually has a sulfur in it. And we're going to find out that sulfur is very important. We're going to see that a lot next semester. We use sulfurs for lipid catabolism and anabolism. Because sulfur is both a good leaving group and a good nucleophile. So we do have a lot of sulfur in our body. I do expect you to be able to know and to draw this, to understand 5' to 3'. You do not need to be able to draw the individual A's, T's, G's, C's, U's, stuff like that, but to be able to draw the backbone and to know RNA versus DNA and what it looks like. Just because it's important, and you're going to see it over and over and over again. It's pretty simple to draw. And the directionality for DNA and RNA is 5' to 3', just like we always talk about N to C directionality for proteins. For nucleic acids, we talk about 5' to 3', assuming that we're talking about the normal, healthy DNA and RNA. Because you're going to find out that there are times that they don't add them in the normal ways. For example, if they cap it, when we talk about capping, it's actually put in inverted. And other non-canonical ways to put things in there. But I do expect you to be able to draw this. And when I say that, I mean, for example, actually we'll just put a blank. We'll put in a blank one, and I'll show you what I mean by that, being able to draw it. So the way that I draw this is I always start off with if I can get the pen to work, I always start off with the oxygen. And many times I know in organic chemistry, if we leave a little stick sticking down like that, we assume it's a methyl. Biochemistry, a lot of times they just assume it's a hydrogen whenever you're drawing the DNA and the RNA. But then when we have to put the little scorpion's tail on for there, of course this is the base. The A, C, G, T, or U. Or it could be inosine, pseudouracil, things like that, but just the base, a nitrogenous base. And if it's RNA, that's the alcohol. If it's DNA, that's just a hydrogen. That's the 3' end, and this is the 5' end. And so now we just put the phosphate. It's got a negative charge right there. And the other single bonded oxygen is going to be the one that's connected to the sugar above it. which I didn't leave myself much room to draw that in. And then this is the 3' end, so draw in our phosphate. And the next sugar. Of course, I don't have enough room to draw in the alcohol. Whoops. Base number 2. And then I have to scoot it up a little bit. We would have the next, so on and so forth, and then this would be the next alcohol. So that's the extent that I want you to be able to draw it and to know what it is. And if I said, to do like an A, G, then it's fine with me if you just wrote A where base was and G where base was. Or if I gave you the structure, I guess you could plug and chug it in. Give everybody a moment to get caught up. This is very, very important. Which is more stable, DNA or RNA? And I want you to know why, under what conditions, why is it biologically relevant, and then why are we not only, DNA or RNA exclusive? Why do we have 2 separate nucleic acids and broad, and we're going to find out that there's different subclasses and stuff. Let me just scoot this over, so that way I can have some, in case I need to draw. So which is more stable? They are not equally stable. Which one's more stable, DNA or RNA? Just in broad generality, everything else is, equal in size, and we're at the same, ionic conditions and things like that. Which is more stable, DNA or RNA?
DNA.
It's DNA. Now, why?
Double-stranded.
So is RNA not double-stranded? Can RNA not be double-stranded? It can. What else can RNA do that DNA cannot do, or not do as much of? So it's not the fact that DNA is double-stranded. We're also going to find out that not all DNA is double helical. There are not going to be any heads left. And so why is DNA more stable? Or you can think of it this way, why is RNA less stable than DNA? Maybe that's easier to answer. So what can RNA do that DNA cannot do or not do as well?
The nucleus?
Pardon?
The nucleus?
No, that's not it.
Does the hydroxyl group have anything to do with that?
Yes, the hydroxyl group is right on. And so what is it about that extra hydroxyl? That's the only difference. So what about the extra hydroxyl group versus the hydrogen? What?
I was going to say it's more likely to bind.
More likely to bind. What kind of bonding and binding can occur?
Hydrogen.
It can do either hydrogen bonding that DNA cannot. What else can oxygen do that a hydrogen cannot do? It attacks things. It can act as a nucleophile. So, and you'll find out there are times that oxygen will actually attack itself. So, so it can actually cleave itself. That's why it can actually adopt many more structures than DNA. That's why you always think of DNA being double helical, and for the most part it is. But RNA can be double helical. We're going to find out RNA can actually be 3-stranded and 4-stranded. Yeah. And so, it can be much more complex. Not as complex as proteins per se, but almost. Okay, so. All right. And so, under what conditions? It really depends. Ionic strength can affect it, can affect its binding. We're going to find out how much water is around, because if it's hydrated versus, even DNA, this is true. If there's more water around or less water around, it can actually cause it to be, more hydrated or dehydrated. The metals, what metals that are around. But now, why is this all, the next 2 questions kind of go hand in hand. Then why is it biologically relevant, and so why are we not only DNA exclusive or RNA exclusive? So, because what is the role of DNA versus RNA?
DNA is long-term, genetic information, whereas RNA is short-term, messages and transferring.
Okay, so DNA is sort of like your backup file, okay? So it's got all your genetic information. You're wanting to keep it. It's the cloud. So you don't want anything to hack into it or anything like that. But by itself, it has very little functionality. Just because you got the information there, it just doesn't do a whole lot. It does you no good. You know, you can have that telephone book. It's got lots of information, but it doesn't do you any good unless you have the ability to open it and understand what the numbers mean. Whereas the RNA does have lots of functionality. Some of it's for messaging. Some of it's more longer term than others. Some of it's very transient. We're going to find out. Just because of the fact that it can adopt many more structures, it has more functionality. However, it is less stable just because it gets hydrolyzed. It gets attacked and falls apart much more easily than DNA. And so that's why you don't, in theory, mRNA itself, the primary transcript has all the information on it too, but it doesn't last, it's too easily attacked. And so then we would all die, get cancer or whatever, die very early on in life because the fact is our genetic information got hydrolyzed too easily, whereas the DNA is more rigid in that sense. All right, so here's just one example of the RNA, as I was mentioning, RNA attacking itself and the way that it's less stable. Now, there are actually times when this is biologically important. There are times that you want this to happen, but then there are many times that you don't. Okay, so what happens here is we have a great nucleophile next to an electrophile. They are vicinally located. They're on vicinal carbons. If you remember from organic chemistry, that means neighboring carbons. And so this is showing it the actual hydroxyl. Of course, we don't have a lot of just, you're going to die if you just drink a bunch of sodium hydroxide. Partly because it's attacking your RNA, but partly just because you're just altering the pH. And so, but there are times that you're going to find out, you can have metal hydroxides. We know we have magnesium, calcium, heavy metals and stuff like that can make hydroxides more prevalent. But you can just have a base in general. And that base can accept the hydrogen and make that oxygen even more nucleophilic. And so we have a boom where it takes off the proton. And then those electrons that were on the oxygen, they can either be an alkoxide and hang around, but many times they're going to attack something. And like I said, it's right next door to this phosphate. And that phosphate's very delta plus since it's got all the oxygens around it. And so it's easy for it to get attacked. And just like carbon, you have to have something that's a leaving group. Technically, you're going to have a transition, not a tetrahedral intermediate. You're going to have a pentacovalent, a 5-membered intermediate, because that's what phosphate, just like carbons have 4 bonds in their intermediates, phosphates have 5. So that phosphorus can do 5 bonds. But you'll have that pentacovalent intermediate, and then you get collapse of it, and you have to have a good leaving group. And we have an excellent leaving group on the adjacent nucleotide. And so you're resulting in a 5' hydroxyl group and what's called a 2', 3' cyclic RNA, okay? And so this 2', 3' cyclic phosphate is the resulting product. And like I said, that's important for certain types of RNA whenever you're cleaving things. When, for example, whenever some of them do the splicing and they get spliced out, that could be the result. Okay. That's not the result of what always happens, though. For example, the enzyme that I worked on, this is what gets attacked. However, it's going to result with a phosphate on this carbon, with a 5' phosphate, and a 3' alcohol on the other portion, because if it attacks on the wrong side of the phosphate, you die. So that's why it's to make tRNA. Your tRNAs have to have a phosphate on the 5' end, or otherwise everything is wrong. So, but this is the most common. Plus, it just shows you how DNA can't do this because there's not that oxygen there. So DNA is more stable for that internal nucleophilic attack, or against that internal nucleophilic attack. Okay, this is what,